going to present on watershed-wide hydrologic restoration, a what, why, and how presentation. My name is Bob Hawley. Thank you for the invitation to speak at the ASCE EWRI workshop down in Austin. And I'm going to dive right in. Begin with the dad joke. What did one stream say to the other? Let's meet around the bend. That's what my kids really like. All right, this presentation aims to bridge the gap between stream restoration and green infrastructure. So here's a screenshot of the program. You just heard Eric and Lindsay talk about stream restoration, trying to mitigate all of those very challenging and extreme problems of stream restoration, of stream erosion throughout Austin. And then after lunch, you're going to hear Matt talk about green stormwater infrastructure. And what this presentation is going to do is show us how we can tailor our stormwater designs in a way that prevents the need to have to do all that stream restoration by holding back those erosive flows and preventing our channels from becoming so terrible to begin with and needing that stream restoration. I have a lot of resources available on our website, including lots of papers and also a guidebook we put together with ASCE. So check that out if you're interested. But to begin, this presentation builds on a previous presentation to this exact conference nearly 5 years ago to the day. And it had a very similar topic, very similar theme, and it was focused on going from the science to the implementation. And what we've realized is that, that's a long journey. It's pretty hard to get to that implementation. So that drum needs to be louder. I must not be the best communicator, but we need to beat that drum louder. And it's not just Austin. You're not alone. We just got back from the 6th Symposium on Urbanization and Stream Ecology. 3 years ago, this same conference, the 5th version of this conference was in Austin. This 6th one was in Australia, and lots of great presentations, lots of really cool research from all across the world. But unfortunately, what we're seeing is still that most stormwater infrastructure still does not protect streams from erosion. So we need to beat that drum even louder. And so that's the goal of this presentation, to really hammer home this key message and show us not only the message, but the what, the why, and the how. So to protect streams from erosion, we need to design stormwater infrastructure to restrict erosive flows. So if we want to not let our stormwater cause this level of erosion, we actually have to use our stormwater facilities to restrict flows that cause the erosion. It's that straightforward, okay? So we're gonna go through again the what, why, and the how on how to get that done, how to get it implemented in Austin. So to begin a brief history of stormwater management, I'm going to borrow some slides from some hydrograph here from Brian Bledsoe from 2002. So under the, this is the 2-year hydrograph, the undeveloped hydrograph, with time on the horizontal, discharge on the vertical. This is from Colorado, but it could really be anywhere in the world where you have, your pre-developed condition, and then basically the post-developed condition. Back previous to the 1950s or so, even through the 1980s, the standard practice for most communities was take that water from your rooftops, take that water from your roads, route it away to very efficient drainage networks like curb and gutters and storm pipes, and get it routed to our streams as quickly as possible. And so you got a lot more volume of runoff because of those impervious surfaces. You're routing it to the streams very efficiently, and that leads to peaks, to increases in the peak discharge. That leads to flooding. And of course, as civil engineers, environmental engineers, professional engineers, we have a responsibility to protect safety of the public and protect property. And so we came up with a solution called peak controlled detention using detention basins, where you take all that extra volume of stormwater runoff, you route it into a detention basin that holds back some of those flows, and those detention basin outlets are optimized in a way that doesn't exceed the pre-developed peak discharge. Right, so all the extra volume has a prolonged discharge that's still pretty high, but it doesn't exceed the peak discharge of the pre-developed condition. So that was our sort of standard of practice. And for 2 or 3 decades or so, we went bananas with our detention basins. Detention basins are ubiquitous in most suburban and urban communities. Unfortunately, those detention basins really, you rarely see them with any water in them, even during rain events and shortly after rain events. And that's because they aren't really designed to do much attenuation of the flows until you get to a pretty big rain event. In most communities, the 2-year event is about the lowest they go as far as flood protection goes. And so our detention basins don't do much attenuation for about 99% of the storms in a typical year. And in some communities, they even have concrete swales in the bottom of their detention basins to make the flow go in and go out very quickly for those more common storm events. And what that leads to in our developed watersheds with conventional stormwater detention, you take a 0.3-inch event, rainfall event in 1 hour, and a small watershed, and it looks like you could whitewater raft this channel, right? But the same size watershed with an undeveloped watershed, same size rainfall, we see very little surface flow getting to our channel. And we actually have a sensor gauge on this that shows that the water depth really didn't change much at all in the stream. And when it did change, it was 3 hours after the rainfall ended. And that just tells you basic hydrologic process where that rainfall was intercepted by leaves on trees. It slowly soaked into the topsoil. And then when it hit that clay subsurface soil, it slowly moved down valley and made its way to the stream. And that stream had very little change in the discharge. So if you're a bug or a channel that is used to very calm reactions to most storms in a typical year, you don't like conventional detention. But if you're concerned about water quality, you also don't like conventional detention, because we weren't doing anything in those conventional detention basins to knock out the first flush and intercept those water quality pollutants. So again, as civil and environmental engineers presented with a problem to our societies, we came up with what I think was a reasonable strategy for managing water quality, where you take a modest volume of rain, and you can intercept 80 to 90% of the storms in a typical year and get that routed to a fairly reasonably sized water quality feature like a sediment forebay or bio-infiltration feature, where you're promoting filtration or you're promoting infiltration, and you're not letting runoff directly into a stream. It first has to pass through some sort of media or go through the ground. And that seemed like a very reasonable strategy from a water quality perspective. And so what a lot of developments did in Northern Kentucky was they took their same old detention basin, they put a sediment forebay on the front, and then they optimized the outlet to meet the flood control standards. And in some more progressive developments, they did things like bio-infiltration basins that had really pretty native plants and really improved the aesthetics for the development. And then in other places, they went even farther. And this is a study by USGS, about a 20-year study of developments with high density of green stormwater infrastructure. They had a forested watershed as their control. They also had an agricultural watershed that was primarily agricultural, but experienced some development later in the study. And then they had 2 treatment watersheds where 100% of the new impervious area was routed to green infrastructure. That was extremely high density of green infrastructure. And it was a treatment train approach where upslope, they had infiltration trenches, tree boxes, underground detention, and then downslope, they had sand filters and dry detention. Okay, so lots and lots of green infrastructure distributed across these watersheds. But unfortunately, the high density green stormwater infrastructure did not protect streams from erosion. The dominant channel evolution model stages in our forested watershed across many channel cross-section repeat surveys. In our forested watershed, the dominant stage is a recovered stage, a stage 5 equilibrium from the Shum model, and with some stage 4 recovering. That's what we saw in the forested control site. In the agricultural site, the dominant stage was stage 4, which is a recovering trajectory. So the aggradational stage. And they also had some of the a few sites that had degradational stages 2 and 3. But then in our treatment watershed, the dominant channel evolution trajectory was degradational stages, stage 1 and stage 3, where you're seeing downcutting, and then you're also seeing downcutting with widening and bank erosion. So here's an example of what I mean by that. So to compare the 2004 channel to the 2017 channel, it got a lot deeper, got a lot wider, right? And it's experiencing very clear degradation, eating up a lot of property and also loading a lot of sediment to the system, right? So despite lots and lots of green infrastructure, most of the channel cross sections in these treatments are experiencing degradation and not the what you'd like to see, which is a recovering trajectory of sort of aggradational processes, or even better, a fully recovered equilibrium condition. And the reason for that is that high density green stormwater infrastructure did not adequately restrict erosive flows. So when you control for the rainfall, so that's on the horizontal axis, and you compare the post-development with the green infrastructure to the pre-development condition, you see that the peak flows were substantially larger, they lasted a lot longer, and the runoff yields were much larger. So despite having lots of good green infrastructure, we didn't restrict those erosive flows. We didn't reduce the peak flows enough. And the big take-home message from this 20-year study, lots and lots of papers came out of it, is that green infrastructure is great, but storage capacity matters. And so green infrastructure that's really mostly focused on water quality isn't going to solve our erosion problems. And we in the civil engineering community have known this for a very long time, that inadequately restricted erosive flows leads to erosion. This is not some environmental activists saying this. This is ASCE and WEF way back in 1992 in our manual of practice on urban stormwater management systems. These are direct quotes where you can read it. If a natural channel is to be used for carrying stormwater runoff, it may be assumed that the changed runoff regime will result in erosion. The effect on the stream increases with the percentage of the watershed that has undergone urbanization. So erosion gets worse the more urban the watershed is. We know that. And the effect on the stream can be minimized by properly designing the components of the urban drainage systems, such as detention basins. Again, that storage capacity matters. But if such increases in stormwater runoff rates are not minimized, the natural streams will enlarge their channels by scouring their bed and banks and generating additional sediment loads. Again, way back 30 years ago, ASCE knew this, right? And many studies document this, that stream bank erosion rates are much higher in developed watersheds. We predicted this. ASCE as a society predicted this, and we see it. This is a Northern Kentucky study where we show erosion rates, changes in width. Streams are getting wider 10 times more erosion, 10 times higher erosion rates in developed watersheds compared to undeveloped sites. And so 1 centimeter per year of widening at our undeveloped sites, over 9 centimeters per year of widening at our developed sites on average. And then not just this is not just Austin also has the same data, is what I'm trying to say. Austin is basically loaded with stream erosion problems. And way back in 1990, based on a lot of good water quality data collection, Austin showed that, as impervious cover increases in the watershed, the TSS load increases fairly linearly to even exponentially, right? The total suspended solids get a lot higher in our urban watersheds, and using that data, they project that greater than 90% of the TSS loads in Austin streams are projected to be from stream erosion. So, and many sediment fingerprinting studies and lots of other studies document the same thing across lots of other sites, or lots of other cities and regions. So why don't Austin's SCMs prevent stream erosion? We've been making investments in stormwater management facilities this whole time, but yet our streams are still hammered, right? And the answer is Austin is not alone. SCMs are not adequately restricting erosive flows pretty much across the world, and the reason is this: you compare when you take a flood control peak matching facility and peak matching idea, and you compare the amount of time above of the hydrograph above the threshold for erosion in the channel. So this dashed line is where erosion begins. If you compare the peak matching conventional detention hydrograph to the pre-developed hydrograph, you have a lot longer durations of flows that are causing erosion. So, imagine hitting a stream with a hammer. You hit it once, a little bit of pebbles move. You hit it 3 times as long, 3 times the particles move, right? So a lot more erosion, a lot more duration of erosive flows means a lot more erosion. And this is not new. We just haven't been able to implement it. But stream erosion is well understood. There's 90 years of knowledge on this, going way back to Shields in 1937, and some really cool stuff at the University of Minnesota on how sand affects stream bed erosion, and you can see these particles, exactly the flows that mobilize these particles, right? So we've been studying this. Geomorphologists and civil engineers, environmental engineers have been studying this for a long time. We got really good idea on this what we call the critical discharge for stream bed erosion, the flow that initiates mobility of the bed, or particle entrainment, however you want to call it. We got a lot of really good knowledge both in the lab and in the field on what flows cause erosion, and it really is this mechanistic link between our community goals like protecting infrastructure, protecting property, and our resource goals like protecting habitat, protecting ecosystems, right? And we've got synthesis studies from the field across Australia and America that show that the critical discharge for stream bed erosion, when you scale it by the 2-year discharge, so you can standardize it and scale it across different size watersheds, it increases with the grain size of the bed. So the larger the particle in the bed, if you're way up in boulders or cobbles, critical discharge is going to be higher. These streams are more resistant than if you're a gravel bed stream or a sand bed stream. So we've got some good data across the world that shows how critical discharge increases with particle size. And we have lots of studies from across the world. This recent one is from Canada that shows that Qcritical is being exceeded more frequently in urban streams. And again, this is basic physics. Anybody who monitors streams and walks streams knows this. You mobilize those particles too frequently, and they're not replaced by particles from upstream. Guess what? Your stream bed downcuts, right? It gets deeper. And often that deepening kind of pivots around these hard points like a culvert or exposed bedrock, but you eventually get deepened and widened stream beds with loaded with head cuts that migrate upstream. Cause lots of stream restoration needs and expensive head cut stabilization projects. But this whole process does not start until you exceed that critical discharge for stream bed erosion. You can't make the stream deeper unless you're mobilizing the particles on the bed, right? So it's a really critical piece to managing erosion. It's also obviously important for water quality. All this water quality, all the sediments, being driven by channel erosion. Uh, and then, biological disturbance. The bugs that live on the bottom of these particles in the stream bed have evolved to natural frequencies of stream bed erosion. And if we make those that a lot more frequent, of course, the bugs are going to suffer. And we know this. We actually have a 7-year study of a Northern Kentucky reference site that shows that, on during sample years when we had that were really close to Qcritical event, our bugs were hammered. They went from excellent to poor at this reference site. But then, years that, the disturbance frequency was more natural, the bugs recover, right? And so basically with increasing time since a Qcritical event, some more time for that particle to be stable for bugs to complete their life cycles, you have increasing biotic integrity. And we see this, that reduced Qcritical disturbance can improve MBI across the full gradient of urbanization. So we all know that MBI, or biological integrity, decreases with watershed impervious area. This is pretty universal. But what you can see, if you look at the data by year across the same region, you see that years that were pretty mild rainfall, and maybe we had a lot more days of stability of the bed. Those years, even our urban sites had excellent MBI condition, right? Years like 2011, when even our reference sites were getting hammered with Qcritical events just 20 or so days prior to the sample, that MBI is poor, right? And our urban sites are poor. But then years like 2007 and 2008, where we had events that didn't quite exceed Qcritical at our reference sites, so they're still really good, but it was enough flow because of the excess stormwater runoff to exceed Qcritical at our urban sites. Our urban sites are hammered. You get this much steeper decrease in this trend, right? So Qcritical really matters for the bugs. And I know there might not be a lot of bug people in the audience, but that matters to bugs and ecosystem and regulators and kids who like to flip over rocks and see the insects. So for Qcritical is really important, but it needs to be calibrated to the stream and region. You see, there's basically 3 orders of magnitude of scatter on this otherwise really nice trend across the globe here. And so luckily, Austin staff have been hard at work putting in the sweat and getting out there in the field and monitoring lots and lots of events across a gradient of Austin streams, setting these bucket traps in, putting these tracer particles in, and monitoring the flows. And so we know, now we know, thanks to all this hard work, that at our least developed sites, kind of our reference-like sites in Austin, the Qcritical for stream bed erosion is 2% of the undeveloped 2-year peak discharge. So 2% of Q2. And so now that's our answer, right? We know the flow threshold that mobilizes these gravels in Austin streams. And again, going back to our key message, to protect streams from erosion, we need to optimize our stormwater designs to restrict those erosive flows that could otherwise exceed Qcritical, right? So how do we specifically protect Austin streams from erosion? We need to design stormwater control measures to restrict all storms that would otherwise exceed Qcritical, right? So not just, some arbitrary or bankful or whatever. It's really all storms that have the potential to exceed Qcritical. Those all need to be restricted in a way that reduces the potential for stream bed erosion to more natural frequencies. So give you an example here. This is a 50-year simulation of storms, and the flow magnitude is on the horizontal axis. The cumulative flow duration is on the vertical axis, and our critical discharge in this system is 20 CFS. In our pre-developed flow regime, so 50 years of pre-developed rainfall and runoff is in blue. So you see over 50 years, we had, about 10 hours of 23 CFS that, just barely exceeded Qcritical, right? And then we had 1 hour of 38 CFS, right? We had, about 0.1 hours of 65 CFS. Well, under the post-developed condition, without any stormwater control, so just basically imagine this as the inflow to the detention basin, we have, basically tenfold increases in the duration of these erosive events. So instead of 1 hour at 38 CFS, we have more than 10 hours, right? Instead of, uh, you know, 0.1 or so hours of 55 CFS, we have 10 hours, right? So all of that extra duration of these erosive flows really adds up to a whole lot of erosion in our channels. Well, the key to Qcritical design is you take all that extra volume that was causing erosion, and you restrict it and you release it below the critical discharge. So that's your magic safe release target. So you take your extra volume and release it less than Qcritical. So you still have events that exceed Qcritical. The 100-year, 50-year, 25, 10-year. Those are still going to exceed Qcritical, but they're restricted in a way such that the cumulative durations of those flows are not exceeding the duration under pre-developed conditions. So 23 CFS, about a little more than 10 hours under pre-developed conditions, a little bit less than 10 hours under the Qcritical detention condition, right? 45 CFS, both a little bit less than about 1 hour, right? So basically the green bars are less than the blue bars, less time at those same flows under the Qcritical detention scenario. But then, what do you do with that extra volume of runoff? If you can't infiltrate it into clay, like we have in Austin and Northern Kentucky, you release it, but you release it in a way that doesn't cause erosion. So all these safe flows down here that are less than Qcritical, those all have longer durations than pre-developed condition, because that's where all your extra runoff gets released, right? So you take all the extra runoff that used to cause erosion, release it at the safe flow below Qcritical. All right, so that's kind of one way to look at it. And that's 50 years of continuous simulation, modeling sediment transport. But this idea of restricting stream erosion potential has been a stormwater management strategy for 21 years. Brian Bledsoe published this in ASC's Journal of Water Resources Planning and Management way back in 2002. And he used this symbol E for the in-stream erosion potential and defined it as the cumulative sediment transport capacity over time of the post-developed regime divided by the pre-developed regime. So in essence, you want your E to be less than or equal to 1. That means that your time integrated erosive power for all discharges under the post-development condition is less than or equal to the time integrated erosive power for all discharges pre-developed, right? So that's the basic idea. And again, it's been around a long time. The unfortunate thing is just has not been implemented that widely. But the good news is that communities that are using this approach are preventing stream erosion and promoting geomorphic recovery. So Southern California requires E be less than or equal to 1 for new development. And where we've got some data coming back after several years post-development, we're seeing these channels recover. So they're showing aggradation. So they're not showing the terrible degradation, lots of channel widening that we saw under the old paradigm. Kentucky, a similar story. Northern Kentucky requires E be less than or equal to 1 for new development. And they're also doing retrofits in previously developed watersheds and showing recovery trajectories in those the streams downstream of those retrofits. Whereas in Melbourne, been doing lots of green infrastructure implementation in previously developed watershed, Little Stringbeck Creek, but unfortunately those retrofits have not been tailored to reduce E to date. And so we're seeing continued degradation in those channels, although they are starting to work towards an E is less than or equal to 1 approach. So they're on board. It's just their retrofits to date didn't quite get there, and that's why they're seeing continued degradation. There's a range of implementation options for this strategy. from more complex, where you require the engineer and developer to do lots of sediment transport modeling for a range of design storms. You could even do continuous simulation modeling if you wanted. But then there's simpler approaches where in Northern Kentucky, what we did is we basically made it a lot easier for engineers and developers to meet this criteria. But in both cases, the key to remember is that what you're doing to prevent erosion is in addition to meeting your water quality and your flood control criteria. So you're still doing those flood control and water quality components. It's just you got one more thing to consider in preventing erosion. And in Northern Kentucky, it's a pretty simple way to implement it. You just take the 2-year post-development and make sure that is less than critical discharge, right? So you're already modeling the 2-year storm, and all you do after you've sized your basin for flood control and you got your water quality controls is you just optimize the outlet to make the 2-year event be less than Qcritical. It's that simple in Northern Kentucky. And in aggregate, what you get when you use this approach and you run a continuous simulation is you get an E of less than or equal to 1 when you meet this simple criteria. So not a hard thing from a design standpoint. Just to carry this out and apply the simple Qcritical approach to a simple 5.5 acre hypothetical site in Austin, we did a review of available site plans, and we saw that most developments use about 10 to 30% of their site for stormwater control measures, and many of them use these partial subfill basins in combination with conventional detention. So we're going to use the same strategy. And a couple notable things here. Small sites in Austin don't currently require 1 foot of freeboard. We're going to go ahead and add 1 foot of freeboard to our designs because we think it's good practice and helps be prepared for events like Hurricane Harvey. And then another, I think this is a pretty cool strategy in Austin, is that they've got detention volume is really driven by the back-to-back storm ideas, where say your detention basin it gets one event, and then 24 hours later you get another event. Well, your storage volume for flood control, the only volume that counts for flood control in your basin is the storage volume that is available 24 hours after the previous event. So if the basin is not draining within 24 hours, the portion of that basin that still has water in it, you can't count towards flood control. So that's a way to be kind of prepared for back-to-back storms. So let's get to it. Here's our current standards. Partial subfill basin here, conventional detention basin here, no freeboard for the 100-year event, and we have an E of 1.4. So the erosion potential of this design that meets current standards today is 40% worse than the pre-developed condition. That means 40% more erosion, which explains why we're seeing streams downstream of developed watersheds in Austin are in this cycle of degradation, right? Lots of down cutting, lots of head cutting, lots of bank erosion, and so forth, because our current policies are not enough to meet to match the pre-developed sediment transport. Now, let's take that simple strategy, make the 4-month storm be released at less than Qcritical, while also meeting the water quality, while also meeting flood control, including that 24-hour back-to-back detention criteria, and adding 1 more foot of freeboard. So we do all that, and with this simple strategy of the 4-month storm being less than Qcritical, we get our E all the way down to 0.32. So it's well below 1, and we would predict that would very likely induce a recovery trajectory. So if we had a system that was like this, we'd see a fairly quick transition, within a couple years or so, to an aggradational trajectory, and then several years later, a recovery trajectory. And not everyone uses the 4-month storm or even models the 4-month storm. So to do the same thing with the 1-year storm, your E would be down to 0.17. And let's say you want to just use the 2-year storm, uh, that will get E down to 0.1. And you're still only using 18% of the site. So still well within that 10 to 30% of the site range, and a erosion potential that is dramatically reduced. If we had E's this low, you could not only be doing more than your fair share of matching the pre-developed sediment transport capacity, but you'd actually start to help induce true recovery and true restoration in these watersheds by reversing the centuries of degradation that these watersheds have experienced from the beaver trapping and the deforestation and the channelization, and then the sediment, the post-sediment alluvium that's accumulated in our valleys from all of our deforestation. So, basically restoring a much more natural flow regime, inducing aggradation to the point where you're starting to reconnect streams to their floodplains, and getting a lot more floodplain connectivity, and so forth. So that's what we would expect with this strategy of reducing E well below 1. And integrating the Qcritical approach into SCM designs is really essential to prevent erosion. Here's an aerial in 1994 of Austin, or 1984 in Austin. Here it is in 2020. You see lots and lots of new pavement out here and down by the airport. And what we know is that if we don't integrate Qcritical into our stormwater designs, we're just going to be chasing our tail. We're just going to be chasing the problem of stream erosion farther and farther out into the landscape, because we know what drives the erosion. We've got the mechanics of it down. And so rather than chasing that problem and seeing more and more erosion farther and farther into our suburbs, Qcritical helps designers tailor those SCM investments to actually prevent erosion. So folks are already building these, investments, these stormwater management facilities. Wouldn't it be great if they were tailored to actually minimize erosion? Qcritical integration can also help prioritize cost-effective restoration in previously developed watersheds. Here's the retrofit case study I mentioned earlier. This detention basin retrofit restricted the 3-month, 6-month, and 1-year storm to be less than Qcritical, reducing E from 18.2 to 10.7, increasing the RBP, or the habitat quality, by 40 points from poor to average. So, this is kind of just showing you proof of concept, and it's really a pillar of watershed scale hydrologic restoration, is kind of capitalizing on these existing stormwater assets, these conventional detention basins that are ubiquitous, plating some of the windows to restrict the flows of those more frequent events like the 1-year, 2-year, 6-month, 4-month, getting those to be released less than Qcritical and be more restorative of a more natural flow regime. If you're interested in other strategies, I didn't have time to get into that, but there's a free paper that ASC just published that talks about some of these other strategies, including floodplain wetlands and hand-placed wood. And so check that out if you're interested in other strategies. But first and foremost, again, the key message: if we want to protect streams from erosion, we've got to design stormwater infrastructure to restrict those erosive flows. Now Austin has the tool to do that. We know the critical discharge in Austin is 2% of the 2-year discharge. We know it still results in basins that are basically in the same size range as the most basins that we see that are getting submitted. So we know it's possible. We know it can be done pretty simply, and so we've got the tools. Let's do it. So I wish you luck on getting this implemented, and I thank you for your interest.